Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about some of these limitations of our solubility expressions. So we've already seen, solubility tends to have a lot of kind of nuance because a lot of things that we say are insoluble still release significant amounts of ions. But even in these more nuanced expressions, we often still neglect a lot of real phenomena. And here I'm going to talk about three key ones that can influence a lot of our answers. So one of the first ones that we've already started to see is going to be the fact that a lot of our ions in these solids tend to be weak bases. So a good example is our good old friend fluoride. So calcium fluoride, well, it releases fluoride. Turns out that fluoride is actually a weak base. It's a weak base with a Kb, now mind you, fairly low, about 6 times 10 to the negative 11th. But it means that it still can release hydroxide in solution. It means it will release free protons. So as a result, we can end up modifying our dissolution reaction by changing the amount of fluoride present in the system by forming hydrogen fluoride. So if I add hydroxide to the system, so if I'm working at fairly basic pHs, then what we end up doing is impeding this reaction. Through Le Chatelier's, I add hydroxide, meaning that very little of the fluoride will react to form HF. And under these cases, we're just fine because then this reaction works exactly how we've seen it so far. However, if I add acid to the system, I'm going to chew up all that hydroxide, decreasing the concentration, making this reaction go forward. This means I've decreased the amount of fluoride in the system. As a result, we're going to increase the solubility of calcium fluoride. And we've seen this already a little bit with hydroxide ligands and adding a buffer. By modifying the pH, we can shift these reactions. However, it's much harder to numerically evaluate the relationship in between pH and fluoride, and it's a little bit beyond the scope of the course. But qualitatively, it's very important to know that we can modify the abundance of these weak bases and occasionally weak acids by changing the pH of the system. Very related is the fact that it turns out that a lot of those free ions that we're releasing into solution aren't going to just remain free ions. So if I take lead iodide, it will dissolve to make, well, lead and iodide. But it turns out that these can complex to make an aqueous lead iodide, which won't have the same concentration as these, or it can make lead monoiodide or lead triiodide or lead tetraiodide. All of these are present in solution. But it turns out that the presence of these extra complexes will reduce the concentration of lead iodide, which increases the solubility, of the degree to which our solid lead iodide breaks apart. Now, it's important to know that this is going to be the qualitative behavior. In order for a more numeric evaluation, you're going to have to combine all of these reactions together. And if you're interested in seeing how real complex systems work, I highly encourage you take analytical chemistry, as this is often a focus trying to figure out how these real complicated chemical systems behave and interact. However, in 2 lectures, we're going to go ahead and start talking about the formation of these complexes and looking at their behavior. And finally, one of the last things we have to include is that it turns out that just because I decomposed and formed an ion doesn't mean that those ions are always going to be available to react and form a solid. So this is due to the formation of what we call an ion pair. So a lot of our cations and anions will form unreactive complexes. So they aren't truly bound, but what happens is we have this cation and anion, which just kind of end up hanging out together, don't really want to go anywhere because it's cozy and they're talking to someone and they're surrounded by water. And so this ion pair essentially reduces the available amount of these free ions to form solids. So it essentially reduces the effective concentration. Now, the formation of these complexes actually is going to have much less to do with the identity of the ions present, and much more about the the total number of charged ions in solution. The more fluorides, chlorides, magnesiums, calciums, sodiums I have in solution, the more likely one of these just pure charge pairs is going to form. And this will, again, reduce the concentration, the effective concentration of any of these ions in solution. Now, one of the classic ways to compensate for this, and we've seen this term before, is to use what's called activity. So traditionally, we said activity for a dissolved species is the same as the concentration. However, when we have lots of these ions present, instead what we use is just use the activity as a methods of talking about the effective concentration or the effective number of these ions in solutions. Now, actually calculating these activities can get quite complex, but qualitatively, the important thing to note is the activities will always be slightly lower than the real concentration of ions present. So the activity of calcium will always be a little bit lower than the concentration of calcium. However, it is worth noting that the activity and the actual concentration tend to grow more and more different as we get higher and higher amounts of ions. And this is one of the reasons why, even though it seems like, according to our equations, last time we had a solubility of magnesium hydroxide of 560 molar, you're never going to quite get there because the activities are always going to reduce the amount of available ions present. So these are going to be some of the key things to watch out for when you're walking through your solubility equations. It doesn't mean that our equations don't work. It just means that occasionally our answers are a little bit more qualitative than quantitative. And if we want to have higher accuracy, we have to take all of these effects into account. Next time, we're going to go ahead and finish up our conversation about solubility by looking at how we can use solubility to separate different ions of species. Until then, take care.